I've been talking so far about closed systems. And now what I'm going to tell you is a section that we haven't updated yet on the notes that we have uploaded, right? But let's see. Let's consider this case. Remember when we talked about getting the water to 100 degrees to make pasta? I had a roommate that would put the water to boil, go to the shower, and come back. And let me tell you, it's not a whole lot of water left after that. Not in the shower, but not in the pot either. So if you forget your pot on the fire, it boils off, right? How long it's going to take? We can calculate that. But to do that calculation, I want you guys to work with me. What control volume should we use? We have a pot. The pot has some water there. We have our fire or electric stove, or better, an induction stove. I don't care what the heat transfer mechanism is. We're putting heat in. And we know that some of this water is evaporating, right? What control volume should I use to analyze this problem? One proposal is this. And by the way, this is not a bad one. This is what I originally thought of using. But we have a problem with this. As we want to make a calculation, essentially what you say, as the steam goes out, you always keep the steam in, right? But it's tough because to calculate the boiling of water from the pot is boiling in air. So this would not be a closed system because air comes in, right? This is kind of a nightmare to calculate that. So this is not really trivial. But what I'm going to propose, right, after having done it both ways, let's put the control volume here. And I'm going to erase this. Right outside the surface. And right outside the surface means what is leaving the control volume is steam. At what temperature is the steam leaving? 100 degrees. So that we know because we put this line so close that there is no heat exchange after. So this is an open system. So what I want to discuss now with you is an open systems, because this brings a super important concept, and the book is not clear on that. And as I prepare for the class, I realize that we ourselves can be more clear. So I want to talk about open systems. So if you remember, we said Q stored between 1 and 2 is M2 I2 minus M1 I1. There is always, this balance is always between 2 points in time. Let's call them 1 and 2, right? If the system is closed, mass is the same, right? Now I want to talk about an open system. So let's say in this open system, as is the case of the pot, let's say I'm not going to do a pot, I'm going to do a potato, more or less. And so let's say this is at a temperature T, whatever, right? And I bring in this new amount of mass into the system. This should not be dashed, right? That is also at temperature T, right? And this is a concept that is not clear anywhere, and I believe it's getting clearer in my mind. But it's very, very important to have it done formally. It will help us understand many things. So here, what I'm going to have is a change in mass because it's an open system. So if both are at the same temperature, right, I'm going to have that the Q stored is I2, whatever enthalpy we have at that temperature, right? So the changing mass changes your heat content. This equation still makes sense from the point of view of math. Question to you, is the temperature going to change as I added more mass, this heat through the mass? In this case, no, right? But let's take this properly. So if we say Q stored, now if we talk about instantaneous balances, this will be enthalpy times rate of mass flow, right? So this would be mass. If we do it instantaneously, would be rate of mass income. This thing in which I add mass across my system and brings thermal energy, this is what is called this is what is called advection. This is the transport of heat through transport of mass. So the book doesn't mentions advection once or twice. It's super important to understand heat exchangers and many more things. So of course I can heat things up with a heater, but let's be aware that if I have a hot bucket of water and I move this hot bucket of water from there to here, I have transferred heat. I have transferred thermal energy too. This example I just made is obvious and it's silly, but let's put it together in the case of boiling a pot of water. All right? So this is then this action we have here, this addition of mass, this is called advection. I'm sure you heard about radiation. I'm sure you have heard about convection, like convective ovens, right? You might not have heard about advection. But the truth is, there is conduction, but there is radiation, but there is no such thing as convection. We have advection, we have conduction, both together. That's what people call convection. When we study a unit on convection, and about a third of our semester will be just on convection, what we are going to see is that in reality, everything we call convection, in reality is a combination of advection and conduction. And we'll understand so many things. In this case, for this control volume, I'm going to keep working here. So we have Q in minus Q out plus Q generated equals Q stored. And under the same comments as before, we're going to say there's no Q generated. But here gets interesting. The Q in we know, right? This is known from previous example. Right? Is whatever heat conduction heat transfer mechanism we have, that's the same. So we know there's no generation. We know the heat in. Let's talk about Q stored. Now we are losing heat by evaporation. Somebody mentioned this earlier today. Let's calculate it. Super important, right? You guys might have heard about evaporative cooling, right? Super important. The difference between humans and most animals as we evolved is that we can run long distances because we have sweat glands. Most animals don't. And because we have sweat glands, we can take water from inside our body, evaporate that water, and keep thermal balance. If we didn't have that, we don't have thermal balance, and we can die of heat stroke. That's crazy, right? Now, what do dogs do because they don't have sweat glands? You know what they do, right? Right? They do this cooling by evaporation through the tongue. It's so amazing, all these things, right? Q out. Let's talk about the Q out. Q out then is going to be the mass that leaves, right, times the enthalpy of the gas, right? This Q out, that is, let's say, is Q advection, right? And because the mass is decreasing, right? The mass is decreasing, but Q out is positive by our definition. I'm going to put this M because the mass rate, right? The total amount of mass in the pot is getting smaller, right? So, and this is enthalpy of the gas. This is the Q out. This is something new. So far, we have never talked about how heat comes in or out. But now, because I just explained to you this issue of open systems and how mass coming in and out brings or takes away heat, which we call advection, we have one mechanism of heat transfer, advection. And here we have the form, right? All right. And what would be the heat stored in this case? So Q stored is and we know is either of these constant in this problem? Remember that we did it for phase change? We said mass is changing, and then we would have enthalpy of the liquid times this is isothermal, right? The water is boiling at 100 degrees. So the enthalpy is always enthalpy of the fluid, of the liquid, always. And what is changing is the mass, right? It all comes from this equation. Right, this is Q in minus Q out equals Q stored. I can put it all together, and I'm going to get Q in equals, I'm going to do it. Anybody can tell me what this is, IG minus IF? Yeah, latent heat of evaporation, right? So this is minus M dot I right? So this is fantastic. And again, we said the Q in that was coming from the range is always constant. So this is constant. This other one, the enthalpy, the latent heat is constant. The heat input is constant. So the mass rate is going to be constant. So we're going to have that we can say this is so if I were to solve for this here, I would get delta M is M2 minus M1. How much is M2 at the end of this problem? What is M2? 0 is the mass of liquid, right? We have no more. M1 is the original mass that we have. That would be volume times density, right? So from here we can solve for time and get delta T equals volume times rho F. And we're going to get, this is density of the liquid times the volume times IFG, right, over Q in, which we have. So here we have our control volume. And here we have the calculation. Again, this is a very easy calculation. I went the long way, so you see every step. This would have been so easy to do intuitively anyway. But going every step. And what do we get? That, yeah, the roommate was taking long showers, because truly it takes about an hour to evaporate a pot of water.